This is Food Chemistry Unit 2. We're still in Chapter 4. Here we're going to look at the classification of matter. There are two general categories. We have pure substances and mixtures. So matter can be broken up into these two general categories. So in terms of pure substances, the basic units are the same. These are your elements and compounds. But how can both of these be classified as pure? Well, elements, which are needed for good health, we'll look at that in a later unit. These are things like Fe, which is iron, Ca is calcium, K is potassium. These are just your elements off the periodic table, right? So that's a pure form of a substance, right? That's just, it is what it is. Those are elements. Now, most pure substances that food scientists work with are actually compounds. This is a combination of the elements like salt, NaCl, baking soda, NaHCO3. So why are compounds also considered pure if you're combining the elements? That's because this combination has to keep its ratio. So salt will always be NaCl. There's no NaCl2 or Na2Cl. That doesn't work. It has to be one Na and one Cl. So any scientist anywhere in the world, if you mention salt to them, they'll know it is sodium chloride and nothing else. Same thing, baking soda will always be one Na, one H, one C, and three O's. So the ratio of those elements cannot change, and that's what makes compounds pure. Now, they are further classified as organic or inorganic, and you might think of organic as something else in the grocery store, which it is. That labeling in the grocery store is different from what it means chemically. So chemically speaking, organic means there are chains or rings of carbons, so really a lot of carbons connected together. All living organisms have carbon. There's actually a whole year of chemistry on this. If you major in chemistry in college, it's called organic chemistry. So there's a whole like subdivision of chemistry related to just organic compounds. So all sources of energy in your diet are organic, and we have a whole unit dedicated to carbohydrates, lipids, and proteins. Inorganic, there's also a year of this division of chemistry. If you major in chem or bio, things like that, it's called inorganic chemistry. So compounds here could have a single carbon in them or really no carbon at all. So examples in food would be H2O, which is water, NaCl, which is salt, and minerals. And yes, we'll look at these as well. Now, mixtures. Most of the substances in food chemistry will be mixtures or not pure. Mixtures are substances put together but not chemically combined. So for example, Ca, that's calcium, it's an element. Salt or NaCl is a compound. Now you don't normally sit and eat these in their pure form. You could take them, I guess, as vitamins, right? Or you could probably taste the salt that you're going to put on your food, but you don't generally like look to eat either one of these in their pure form. They're usually mixed together in a substance. Milk, for example, has both calcium and NaCl, and mixtures are further classified as homogeneous or heterogeneous. So let's look at homogeneous first. A homogeneous mixture will have a uniform distribution of its particles in the sample. So visually, you cannot tell what parts are in the mixture. So if you think about milk, like you can't see where the calcium, proteins, fats, sugars, or anything are just by looking at the milk. Kool-Aid, same thing. You can't tell the sugar from the water or the flavoring packets, right? Especially if you buy it like this, you really can't tell the parts. And then your juice box is the same thing. You can't tell the different parts of the juice as you are drinking it. It should taste as just the juice itself, right? This is often referred to as a solution. Usually has a solute, which is a material dissolved like sugar, dissolved in a solvent. It's the material that does the dissolving. And we'll look at these parts a little bit later on in more detail. All right, heterogeneous mixtures have a non-uniform distribution of particles in the sample. So visually, you are able to determine the different parts of the substance, like vegetable soup. You can tell the vegetables from the broth. Frappuccinos, you can see like the coffee or like fruit flavored part versus like the parts that are in there, like Java chip, or the whipped cream versus the sprinkles. Oil and vinegar dressing, right? Especially if you let it just sit and don't shake it, the oil and vinegar separate from each other so you can tell the parts. Heterogeneous mixtures are also known as suspensions. Suspensions have undissolved particles. So like orange juice with the pulp, you can see the pulp in the juice, which is the bits of the orange. chocolate chip cookies, you can see the chips in the dough. All right, fluids can have characteristics of gases and liquids. So if you take a non-Newtonian fluid, so this is a type of mixture, right, but we call it a fluid. It has characteristics of liquids and solids, this non-Newtonian fluid. It's really cornstarch and water, which might sound familiar to you, but you do often add that to sauces and gravies, but you need to be careful. If you add 2 parts cornstarch to 1 part water, you get what's called oobleck, and that's where the non-Newtonian fluid term comes from, right? It can be poured slowly, acting like a liquid, but if you let it sit and then you apply a force to it, like pounding with your fist, after you pour it on the desk or in a bowl, it acts like a solid. And you may have made this in chemistry or physical science. It's very funky to mess with this, but you don't want to use this for cooking. If you want to use cornstarch and water in cooking, you need equal parts of both. It's often called like a slurry or a paste, something like that. All right, colloidal dispersions. So in some mixtures, the particles are dispersed in liquid without being dissolved. Mixtures in which microscopic particles are evenly distributed in another are called colloids. We'll look at emulsions in just a second, but these are emulsions, foams, and gels. So what does this mean for you in terms of food? Think of your jelly, right? Mayo, butter, and gelatin. They're all kind of funky-ish solids, right? This you can actually break it with a spoon, right, and eat it, kind of dissolves in your mouth as soon as you start to eat it. Butter looks like a solid, but you can spread it. And then both of these two are mainly solids, right, in the jars, but they're both spreadable. Now, in terms of particle density, in some mixtures, particles do not remain dispersed, and this is based on the density, right, mass per volume of the particle. So like flour and water, when you're baking, right, that flour is not evenly distributed. You can see the clumps. Or how about the fat in milk that's not homogenized? This would basically be milk from the animal itself without doing anything to it. If you let it sit for a while, the fat would separate from the milk. So let's look at milk, because we're going to use this in quite a few of our labs. We talk about milk quite a bit. Milk is a colloidal dispersion, and it is also a solution. It's a solution because you have sugar, minerals, proteins, and fat all mixed together. But in terms of the colloid classification, there are proteins, those are colloids, dispersed throughout the milk. Fat is not a stable dispersion. It will rise to the top like film on gravy. You might know it as cream. So that's why our milk in the US is homogenized to prevent this. So what that means is milk is forced through screens to break up the fat and prevent it from rising. This fat is now known as an emulsion. Okay. All right, so emulsions. These are mixtures of 2 immiscible liquids. So immiscible means that things will not mix. So an emulsion is you are attempting to mix 2 things that should not be mixed together. So one is dispersed in droplet form and another. It's usually 2 unlike substances, and from chem we call this polar and nonpolar. So we had rules like dissolves like, things like that, right? So polar and nonpolar don't like each other. So this is like oil and water. This would be your salad dressing, right? So this is what's called a temporary emulsion, right? You have to shake the bottle for these 2 to come together. But if you let it rest, you can see in this bottle right here, they separate out because oil and vinegar don't like each other. It's based on polarity. Now, to keep unlike substances together, you could add an emulsifier. So lecithin in egg yolks, that's used to attach molecules of oil and vinegar together to make mayonnaise, right, which is an egg-based product. Lecithin in chocolate bars, that keeps the cocoa powder and sugar evenly distributed in the cocoa butter. And there are 2 types of emulsions. You have your oil in water emulsion. So oil is dissolved in a water solution. So you have more water than oil. This is something like mayonnaise, salad dressing, which we've seen, but how about your ice cream, right? And your cake batters? Then you have your water in oil emulsions. So there's more oil than water. Butter and margarine would fit into this group. Cream is skimmed from milk, which is fat and protein that was suspended in the milk, right? So you can pull that off. The particles are agitated, clumped together, and that's your butter. So right now I told you milk is homogenized, right? but you can actually pull that cream or fat out of the milk, and that's kind of one of our labs. And you can use that fat to go on and make butter. So first you can get whipped cream, and then if you keep going, you get butter. So oil and water emulsions. This is oil dissolved in a water solution. There's more oil than water. Again, it's your mayonnaise, salad dressings, ice cream, and cake batters. So let's look at butter. This is formed from whipping cream. The fat in the cream is surrounded by an emulsifier or lecithin. To break the fat and emulsifier bond, you need agitation. So you could use like a hand beater, right, or a blender or a mixer. The clumps of fat will separate from the liquids of the cream, and you have butter. And butter is about 80% fat, 20% water, and milk solids. So this is what it looks like, right, after you beat the milk like for a long time, and then you could form it into these sticks of butter. Water in oil emulsions. Butter is formed from hydrogenated vegetable oil, right? So there's a lot of claims that it's so much better for you than butter. It's really just coming from oil instead of an animal, which is where butter comes from. So it's 80% fat from vegetable oil, along with water, emulsifiers, salt, butter flavoring, color, preservatives, and vitamins. The ingredients will either dissolve in the water or the fat, and then the mixture is agitated like butter, and the result is margarine. And in terms of low-fat margarine, basically the water percentage is increased. All right, so temperature would affect the stability of emulsions. There's something called hollandaise sauce. I'm not a huge fan of this, but it's right there in the picture. You usually see this on Eggs Benedict, which I've never eaten. I know what it is, but it's right there on the top of it. So this hollandaise sauce is an emulsion that can become unstable and curdle due to high temperatures. So you got to be very particular and careful when you try to make this. So that sauce is made of egg yolk, butter, lemon juice, water, salt, and pepper. So 170 degrees Fahrenheit is the best temperature for the sauce. But check this out, if you heat it to 180 or 190, right, 10 to 20 degrees higher, that sauce will curdle and separate. So a lot of times in cooking shows, people say like that the sauce breaks, and that's why, because temperature does affect the stability. All right, ice cream. This is a water-based sugar solution. It forms an emulsion with the fat-based cream. Again, here's the agitation, right? So you have agitation as it freezes. This adds air to the emulsion. The water freezes. The concentration of sugar increases. The solution would become gritty if cream was not added. So cream kind of smooths it out. So the fat from the cream actually helps prevent this. Emulsifiers are added in commercial ice cream to keep it thicker. But in fresh ice cream, you don't need that because you eat it right away and it tastes really good. Also gums, pectins, and lecithin. This keeps the cream and the sugar from separating as well. But you really need this again if you're going to keep it for long periods of time or like for commercial use. All right, and foams. These are colloids of gas or air bubbles dispersed in a liquid. So this is your froth on root beer. That's an unstable foam. It does not last long, but it tastes really good. Meringue, right? Whipped cream, whipped toppings. These are more stable and will last longer. And there's many factors involved for foam stability. So they're not easy to manage. They can break because again, there's a lot of factors involved for their stability.